Happy Movember, and welcome to the last part of the quantum topic for IB physics. Before we were dealing with radioactive decay, but we kind of were doing some easy stuff. And now we're going to get into the decay constant, and we'll discuss how that decay constant relates to half-life, and we'll even talk about how scientists would actually go about measuring the half-life of an isotope in real life. Now, you should know that if you have a graph of n, which might be the number of undecayed nuclei, or maybe parents, on your y-axis, and you have time on your x, you should know that you are going to get this type of function, and this is exponential. Duh. If you don't know that, demotion. IB bio for you. Now, something you may not know about, though, is that this exponential function is highly governed by the decay constant. Now, take a minute and pause it and write this definition down. Now, also, you should be well aware that the decay constant gets the symbol lambda, same as what you would use for wavelength. So here's our definition again. And if you look at what it's saying, if this is the rate of decay right here, and the decay constant is equal to this rate divided by undecayed nuclei, which is this here, what you can see is if you have something that has a high rate of decay, which would be this here, that would mean that this number, the decay constant, is going to be high. So if something's decaying very fast, has a high probability of decaying, that will have a large decay constant. What you can do with this equation is this can be rearranged as dn over dt. If you then do some magical calculus, which you don't have to know how to do, and you integrate this, you get the magical function here, where the undecayed nuclei that you have left is this. This is your original number of undecayed nuclei, this n sub 0. You know what the decay constant is. This is your time. And this is how you end up with your exponential function. Something you have to do is you have to do a derivation. Let me tell you how excited I am about this. And show how you get this relationship over here between your decay constant lambda and a half-life, which we're going to call t over 1/2. You have to be able to start with this thing here. Probably thinking, how in the world are we going to do this? Well, buckle up, because here we go. If you rearrange this and you end up with n over n sub 0 equals the same stuff on the right side. This is your number of nuclei that you have left that are undecayed compared to your original. At 1/2, at your half-life, the ratio between these is going to be 1 over 2. And that is when you've gone through a time of 1/2. Now, you have to be pretty clever to figure this out. You take the ln of both sides, that crazy natural log, and then you end up doing some magical math that hopefully you learned sometime in life and you thought would never be useful. It's useful now. You can do that. And you take the ln of the e side. I don't know how it works, but it does. You end up getting rid of your e, and you get this. And then, let's switch colors just to make it more exciting. The ln of 1 is 0, and you end up with, let's go up to here, negative ln 2 equals negative lambda over t 1/2. And let's just end up by saying t 1/2 equals ln of 2 over lambda. Hey, how about that? We're done. You can even take this one step farther and work it out on your calculator. ln of 2 is 0.693 over lambda. Ba-boom! Derivation complete. Oh yeah, quick fact you need to know about the decay constant. This is your decay rate on top, just number of atoms on bottom. The units will be disintegrations per second. Or you can drop the disintegrations and just know that it's in per seconds. You might ask yourself, when scientists are trying to find the half-lives of these elements that have a half-life of a few 100,000 years, do they actually wait around for 100,000 years? No, that'd be stupid. What they do is they do something clever, like making a graph of time versus the natural log of the number of undecayed nuclei, and then the slope of this is lambda, the decay constant. And once you have the decay constant, you can find the half-life. And you might think, oh, that's really weird and strange. I have no idea how that would happen. Well, let me show you. You start with this equation, and then here comes that crazy natural log again, both sides. And you end up with this situation here. And you have this happening. You get rid of your E, and then you rearrange it to the form of this. That wasn't a really amazing rearrangement there. And then this, let me just switch colors here. So the form of y equals mx plus b. Here's your straight line. That's your y-axis. Here's your intercept. And here is your slope. And that's why the slope of this tells you lambda. As if you didn't have enough equations in this part of it, do also remember that we have the term activity, which we call capital A, which is equal, or the same thing, as this rate of decay. Now, just to backtrack a little bit, if you remember this equation here for the decay constant, we can actually plug in A here. So that means we can say that lambda is equal to A over N. And so then what we can say is that activity is equal to decay constant times N. And if you even remember this crazy equation that we had from before, you can plug this into N if you want. And we have one final useful, although kind of annoying equation, that this must be true. This is a useful equation also. The end.